as a speaker. It's my great pleasure. Max is a research chair in machine learning at the University of Amsterdam and also vice president of technology at Qualcomm. He also has a secondary appointment as a senior fellow at Cypher. And in terms of academic services, he has probably held all the prominent roles that you can think of: board member of Neurops Foundation, associate editor-in-chief of PAMI, more recently also founding member of Alice. And I think we can safely say that with an H-index of 70, he is probably one of the most influential AI researchers of our time. So today, Max will talk about his research on graph neural networks. If you have questions, please post them online. You will see the bottom at the webpage from which you're watching the stream. I'm not sure what. Now it's gone. Please, Max, the stage is yours, and maybe everybody else mutes their mic.
Okay, great. Thank you, Lena, for the kind introduction. This is my first Zoom, or actually not Zoom, I guess, sort of talk that I'm going to give. So I hope it's you feel engaged and you enjoy it, and things go well. If you have questions, please put them in the chat, and the chair will sort of ask them at the end of the talk. Okay, so the red thing here is going to be my pointers, the laser pointer, and I'm going to talk about graph neural nets here today, and I have basically two parts. One is about equivariance, and the other one is about hybrid neural nets. And as usual, the big brains behind these projects is not me, but are my very talented students and colleagues. So for the equivariant mesh CNNs, there's Pim de Haan, Maurice Weiler, and Taco Cohen, who I have been collaborating with, and it's been a great pleasure to work with them. And on the neural augmentation for graph neural nets, I've been working with Victor Garcia. So the first team is in Qualcomm and Cuba, and the second team is a Delta lab, which is sponsored by Bosch. Okay, so the general topic of my talk today is a geometric deep learning. And so the first question we might want to ask is, what is geometric deep learning? And it's basically developed to deal with data which is non-Euclidean or lives in non-Euclidean domains. And there's many data that is not of the kind of a sequence or a image or maybe a 3D volume of some kind, like MRI imaging. But maybe it's like data that lives on a sphere, for instance, the weather data on the Earth, like if you want to predict storms or something like that. Or it could be data that lives on a graph, like social interaction data or protein-protein interaction data, right? And so deep learning has been incredibly successful. And so one of the reasons it's been so incredibly successful is basically because of this concept of convolutions. And one of the questions that we ask in geometric deep learning is, can we generalize this idea of convolutions on these non-Euclidean domains? And that's what's called geometric deep learning. And there's been a lot of things developed already in this field that go under the names geometric or graph or group or gauge convolutions. Today, I'll be talking about graph convolutions and also a little bit about gauge convolutions and group convolutions. And there's many application areas, as I said, both in computer vision and graphics and social networks and chemistry and biology and physics and medicine. And so I hope a lot of these things, these techniques will find applications in all of these exciting domains. Okay, so if I needed to describe machine learning in one slide, it would be this slide. And it's, in my opinion, the fundamental trade-off of machine learning is basically there is two ingredients in a prediction machine. One is inductive bias, which is our preconceptions about how the world works, and we encode those in models. And then there is the data, right? And both of these, a combination of these two, through training, will turn into a model that makes predictions. And there's some kind of spectrum here. So we have on the one end of the spectrum, we have models where we cannot collect a lot of data for, and often in the medical domain, this is exactly the case. You might have only a couple of hundred, let's say, MRI images for a particular disease that you want to model. And there we need to inject a lot of inductive bias in order to make these models make good predictions. And there we typically think about generative models. So in generative models, and I will go a little bit deeper in what those mean, we can, all the variables have meaning, the interactions have meaning, and so there's typically not a lot of parameters, and basically these are causal models or models based on physical interactions and stuff like that. And they're pretty good at out-of-domain generalization. So we can train these models in one domain, and they typically, if we do it well, can also do quite well, if we slightly change the domain. On the other side of the spectrum, there is like a huge amount of data. Like think about sort of image data or sort of text data where we want to do sort of automated machine translation. And there, deep learning really shines. The advantage is that we can make really good predictions, but the disadvantage is that we need lots and lots of data to make these models work really well. And also we need to define these things on a fairly limited domain, because the bigger we make the domain, we almost exponentially need more data to cover that domain. And so typically these models are not really good at out-of-domain generalization. So these are the trade-offs that we have. And so the big question is then, the name of the game is, how can we inject the right inductive bias into our models, right? If we put the wrong inductive bias, clearly we have biases that are not going to be very helpful for making predictions. But if we get the right inductive biases and just enough of that inductive bias, then we can make really good models. And how can we combine this with deep learning? And there's basically two ways that we've approached this. And I'm going to talk a little bit about both of these strategies. The first strategy is what we call sort of symmetry. So identify symmetries in the world and try to bake these symmetries into these neural networks. And of course, we already know that convolutions are basically an expression of translational symmetry. So we understand that, if we try to detect an object on the left upper corner of an image or the right bottom corner of an image, it's still the same object that we want to detect. And so there is a sense of translational symmetry. And if you work through what that, mathematically, what that would imply for a neural net, if you start from an MLP and you add that particular symmetry, you'll get to a convolutional neural network. But that's translations. Can we also do rotations and maybe scalings, which is just slightly different? It's not a group, it's a semi-group if you do it on pixels. And another example is, for instance, permutation. So if you have a graph, then if you represent the nodes of the graph as a vector, then the ordering of those nodes is immaterial. It's a symmetry, and so you really want the outcome to be independent of how you ordered those nodes in this vector. And so the symmetry group now becomes the group of permutations. Okay, that's one part of the talk. The other part of the talk is about this idea that the world is really simpler in the generative direction. The physical world, there's physical laws. The laws of physics are surprisingly simple, especially at the micro level. Of course, causation happens in the generative direction. So if we think hard about how the data is generated through the sensors, for instance, then typically these models, they're easier. They require less parameters to write down. But deep learning sort of works in the opposite direction, as I will explain in more detail later. They work in the opposite direction of the causal direction in some sense. So one natural question is, can we add this generative causal information that we have about the world into our neural networks? And so that's the second thing. And one area that we applied it to is MRI sensor, MRI image reconstruction from few input measurements, and the other one, for instance, is channel decode, so error correction decoding using a noisy channel. So now let's talk about part one, which is mesh, equivariant mesh CNNs. And let's first review again what a convolution really is. So if you have like a neural net here at the bottom, it's a bit small, but it doesn't matter. There's a couple of operations in between these layers, and these are, typically of the kind, the convolutions plus nonlinearities. And here I sort of animated, or Vincent has here animated what a convolution look like. It's a linear operation. You have a little filter, which is this 3x3 template here, which you slide over the image, and then you take the inner product between basically the values of the filter and the underlying image, and you add them up, and then you store the result in the sort of the array one level above. And then you do a nonlinearity, and then you repeat this process, possibly also with some downsampling or pooling operation, before in the end you put everything into a big vector, and then you add a sort of an MLP neural net, and then you make predictions. Okay, so that's a convolution. A slightly different way of looking at a convolution that's useful for us is as a message passing algorithm. So now we don't typically have one of these things, but we have a stack. So here at the bottom, you see the stack of feature maps. So if you take one pixel and you slice through, all this stack here for this particular pixel, this is the pixel. So you get a stack of sort of values here for one for each of these feature maps. So this little vector living on each one of these nodes. And what we do with the convolution, at every point in the image, every node collects information from its direct neighbors. It sort of queries the values of the neighbors, and it then multiplies that vector that's living here with a matrix W1. It does that for all the neighbors and itself, and then it adds all the results together to get the value at H0. And the important thing to note here is that these matrices here can all be different, because north, east, and north, south, and west, they're all different, and they will also always be different for these for images. Now, if you go to graphs, the situation is actually a little different. So here you see again what a normal convolution looks like, but for a graph, it's much more irregular, right? So first of all, the number of neighbors could be different. So where here you have always the same, 8 neighbors. Here, for this node, the number of neighbors could be very different than for this node. And so now, and moreover, I could sort of, if I have ordered them like 1, 2, 3, 4, 5 in that order, like I'm doing here, 1, 2, 3, 4, 5, etc. Right? In a graph, if I just move these two around, keeping the X between them, I sort of move this guy here. Now the order is different, but it's still exactly the same graph. And so we really can sort of have different messages for each one of the neighbors, because the neighbors change all the time and their number changes. And so basically the solution has been to just send the same message from each one of these neighbors. You sort of get out of this problem easily by sort of sending the same message by all of the neighbors, and only the guy in the center can send a different message to itself. So that's actually what a graph neural net is. It's very simple, and it looks a lot like a normal convolution if you view it this way. So if you think of it, a graph convolution like K star F at a point P, then there's this self matrix here, which multiplies the feature at the point itself, where we're going to collect the information with a matrix K self. And there is this sum over all your neighbors, where we have the same matrix K neighbor multiplied by the feature vectors at the neighbors K. But it's important that this K always has to be the same K. It has to be shared. And this has, in fact, led to a lot of discussion in the community. Is this actually a powerful enough sort of architecture? And it turns out, some people were skeptical in the beginning, and later it turned out that it is actually a pretty powerful thing anyway. And this is not the most general thing you can write down, but it is pretty powerful. But it's, for graphs, basically, it's the right thing to do. But now we wanted to ask the question, what if what you're interested in is not a graph, but it's more like a mesh? And of course, there's a difference, because a mesh is sort of a discretization of a manifold. And so here you have a meshing of like a dolphin, right? Why I'm talking about that here as well is that in the medical domain, you often see when you do sort of computational models, you often see that people do mesh for instance, a beating heart, or in this case, in this paper, it was arteries that were being modeled by adding a mesh on them. And then you can sort of, try to predict certain sort of properties of arteries like this by doing a graph convolution on this graph. It certainly looks like a graph, right? There's nodes and there's edges. And so you can just apply like a graph convolutional neural network for, in this case, coronary artery segmentation. And then here's another example from these guys here for 3D shape analysis. Again, it's a meshed object, and they used a graph convolution. But the main point that I'm going to make here is that, in fact, it's a bit limited to do that. It's not wrong, but it's a bit limited in the sense that this completely ignores the underlying geometry of the problem. In other words, it ignores the fact that a mesh and a graph are really two different things. And so to give you an example, if you would do a graph convolution in this part here, so we have a point P in the middle, and we're sending these messages from the neighbors to the middle, then this situation for a graph would look exactly the same than this situation, because it's still the same ordering, and it's the the same messages that are being sent. But the geometry tells us that there's an angle here which is bigger than this angle here. So the geometry is actually different, but the graph CNN would not see it. And so the question is this actually the right way, the proper way of doing it? Now, you could think, well, we should really, just take what we ordinarily do for convolutions on a plane, like here, and just try to discretize that, on the manifold, on this object, and then try to just think of it as a discretization of a normal sort of convolution. And then you run into issues fairly quickly. And let me try to tell you why there is issues when trying to do convolutions on manifolds. So if you do a convolution on a plane, then you start, let's say, with some kind of filter, like here, right? And then you want to share that filter with another position in the plane. So this is this sort of the translational sort of property that you want to take some filter and you want to move it to some other place and then share it. And in a normal convolution, it doesn't depend on the path that you take. You basically, whichever path you take, if you translate this thing to here, you get the same answer. But the problem is that if you do it on a sphere, right, then in fact, this is not the case. So in a sphere, if you take your sort of filter here and you want to move it here, so you see that you have to sort of parallelly transport it to this particular position. But if you take it along this path here, from here to here, then in fact, if you now compare the two, then you see that the orientation is completely different, right? From here to here, the orientation is actually very different. And so you're sort of into trouble because now you cannot really meaningfully sort of in a unique way share this filter with any other point on the manifold. And maybe even more dramatically on a Möbius strip, you get something similar where if you parallelly transport this filter, you go around this thing, then in fact it becomes back mirrored when you're around, right? And so there's no unique way even to define the handedness of this particular frame. Okay, so that's something that we really have to resolve. And the way we're going to resolve it is to say, well, there is a particular symmetry in this problem. We can not in any way sort of distinguish, in this case, the orientation of the frame. We have to just consider that asymmetry of the problem. We have to basically make sure that whatever we do, we know how to transform from one frame to the other frame if we rotate it. And here it would be the handedness. Okay, so that brings us to the concept of equivariance. And in equivariance, we basically say that if I have some function that goes from x to y, so this could be our convolution, and I have some transformations that act on x, this could be a rotation or a translation, both in x and y space. then we can say that f is equivariant if this particular diagram commutes. This, if I first do my convolution and then I do my rotation, it should be the same as if I do first my rotation and then my convolution. And in translations, in terms of an image, you can very clearly see that that's true for a convolutional neural net. So if I take an input image and I convolve it, so that it's going to get a filtered image. If I translate it, this particular gecko moves here. And if I then filter it, I get this. And this will be the same thing as I take the filtered gecko and I translate it. It turns out that this particular equation, this equivariance equation, is enough to sort of, in a consistent way define sort of the convolutions under these kinds of symmetry operations. And to give you a little bit more sort of intuition of what equivariance means, so let's have in this case, a special group. So the group would be the group of 4 rotations over angles of 90 degrees. And so here I have an input image, and here I rotate my input image. And here I have my sort of convolutional operator. So my convolutional operator in this case does 2 things. It is an eye detector, and it detects the eye under 4 different orientations. So it takes this filter, but it rotates the filter under 4, again, these 90 degrees rotations. And there's a mouth detector, which also we rotate it under 4 times 90 degrees. And then what you see is if you, let's say, okay, you have this input image and there is an eye and clearly there is a mouth. And so our filters detect, they fire at these positions and this position. Okay, now what happens if I rotate my image? Then what happens is that, first of all, of course, the eyes and the mouth are rotated. And so what will happen is that not the first one will fire because this eye was up, at the wrong orientation for this particular image. So now this particular stack of sort of features will fire. And that means that not only, so 2 things have happened. First of all, we did a rotation in the feature map. And secondly, we moved from this stack of feature maps to the next stack of feature maps. But anyway, it is a predictable transformation. And we can show that if we first do a convolution and then a rotation, it's the same as first doing the rotation and then the convolution. And so that is an equivariant operation. Sort of maybe more abstractly, you can view it this way. So I have a particular point X, which could be an image. There's one point here is an image. And I can rotate the image. And so that's the orbit. Here's the orbit of rotating that image. And at every point, I have a particular, let's say for that image, I have a particular feature vector, which is, this shown as this particular sort of line here. Now, if I rotate around, right, I basically, this vector here moves to this position, right? And the vector itself also rotates because it's pointing inward, and here it's pointing inward too. So this basically means that the vector Rx at the rotated point X for the stack, this is 1, 2, 3, 4. So you can also think of 1, 2, 3, 4 circles. At this particular value here, at A plus R is a rotation of the vector at XA. And that's what we call equivariance. Okay, so how does that now look for a mesh? Because this is sort of this is what we call the group convolutions. And now, how do we do this for our meshes? So here I have a little meshed up sort of bowl. And so at the middle, I have point P, and I want to collect my sort of information at this point P by doing a convolution. So the first thing is that I will have to define a gauge. I have to define, where is the angle theta equals 0 in order to do my convolution. So what I'm going to do is I'm going to move these points here actually to, what we call the tangent plane. So we move them to the tangent plane of this particular point. So that's depicted here. And we have to then pick a angle that we assign 0. In this case, that's the green point. So we just pick one of these points arbitrarily, and we say that's angle 0. And then the situation looked like this. So now we do our convolution, and it turns out in this particular case it's a graph convolution, and so it's isotropic, and so we get some answer here in the middle. Now, I could have also picked another gauge. I could have said, well, instead of the green point, I'm going to make the red point theta equals 0. And as I said before, there is no meaningful way, no unique way of doing this. So the answer then is let's do it for every possible way, and then to at least figure out how these things, map to each other, how they transform to each other. So the other option I could have chosen was, okay, take the red dot to be the sort of the angle theta equals 0, do our convolution there. So this basically means now we're sending these messages here, and we get some information in the middle, okay? And now these two things have to be related to each other. So we have to give, in this case, the same answer because it was a graph convolution. And indeed, graph convolutions, because because it's isotropic, they send the same message from each one of the neighbors. That's exactly what will happen. Now, for a more general setup, which is our mesh convolution, in this case, we have a little vector living, it's not just a single point, but we have a little vector living, on these points. We have a vector signal. And so again, we have the same situation that we could pick, either the green or the red point as our theta equals 0. But now, if we're going to do our convolution, the end result could be like a little vector sticking out in this direction if we do it in this gauge. But the problem is that this is a rotated frame, if you compare it to this one. So here, the vector would actually be pointing in a different direction. And so now we get a result which is sort of depends on the gauge that we chose, and we already decided that's arbitrary. So what we need to do, we need to show is how do these two things relate. So if I know this and I know this and I know how these two would transform, then I'll be good too. So equivariance would be saying, if I would do my convolution here in this particular gauge, and then I transform, it would be the same as doing my convolution here, or first transform and then do my convolution here. And again, we have a commuting diagram. Okay, so maybe in terms of equations, let's first review again the equation for a graph convolution. So I have a particular feature vector f living at the center node P, and I have some matrix which multiplies it. And I add to that sort of a single matrix K multiplied by the feature vectors of the neighbors, and I add them all up, and then I get my convolution. That's what the graph convolution was. And it is isotropic because this thing is the same message sent from all neighbors. So it's sort of this case on this side here. Now we're going to generalize that to this equation. And the only difference is, it turns out, is that we can, there's two differences. This difference here is that this matrix, these messages that were being sent, can now actually depend on theta. It can depend on the angle from which the message was sent. And that's important because now the convolution is no longer isotropic, which means it's more powerful. It's a more flexible sort of filter that you can use. And the other thing we have to do is this row matrix. Now explain now what that row matrix is. But that basically tells us that it has something to do with parallel transport. Okay, so in this case here, again, we have our basically example on a flat manifold. So let's look at the flat situation. I have some vector here, and I have some gauge defined by, basically putting the orange line here to the theta equals 0 map. And then I'm going to transport this particular vector in the plane here. So it's parallel. So that's just parallel transport. But here I might have chosen a different gauge, right? So here I chose this as the sort of the theta equals 0 line. But let's say at P, we might have chosen a very different gauge, which might be this one. And again, this is arbitrary. So then, even though in this space things look nice and parallel, in the space of these coordinates, actually this vector has rotated, right? So this vector that was like this here is now rotated like this, and that's just because we chose a different frame. Okay, so we need to compensate for that, and that's this row. Part of what this row does is exactly compensate for that. Now, there's one other phenomenon, which is that if we parallel transport on a manifold, then parallelism is a bit tricky. So in this particular case of a meshed up sort of manifold, you have to look at the tangent plane, and the tangent plane, you have to define in a particular way. But let's just think of it some kind of plane which is sort of, on the tip of this point. It's equilibrating at the tip of this point. And so here it's this particular circle here, the solid circle, that's the tangent plane defined there, right? But in order to move it, I first have to rotate this plane in this direction to make it in the same orientation here, and then move it, right? So there's just two operations. I rotate and then I move. And this is basically on a manifold. The parallel transport is a bit more tricky than just in a planar situation. But it's well defined, and so again, I have this parallel transport by rotating this and then also moving to the new frame. And all of that is absorbed in this row matrix. So I take my feature at the neighbors, I then transform under row, which is these two operations, and then I take the inner product with my sort of filter, which now depends on the theta. Okay. Yeah, I just wanted to leave it at that. We've done interesting experiments to show that this is actually more general than a normal graph CNN, and because we can make these filters now anisotropic. And it's not all that complicated, as you see here. It's not like a very complicated algorithm, but it has this beautiful equivariance property. Okay, so then the second topic I want to talk about is another way to inject inductive bias into our models, which is what I call neural augmentation. And the first thing is to sort of think a little bit about the difference between generative forward models and inverse models or deep learning models. And basically, a generative model is a model that imagines how the data gets generated. So it sort of models the data generation process. Like here's two galaxies which are colliding under gravitational forces, right? And we know all the laws of physics, and so we can basically simulate it. So a simulator is one, kind of generative model. Now, graphical models are more popular, have been more popular in the machine learning community as ways to define generative processes, right? So here's a graphical model that tries to depict, how, like, let's say, documents are being generated or something. And then there's probabilistic programs, which is basically an extension of graphical models, where you try to encode that into some kind of programming language where you can very nicely sort of specify which distributions you want to use, et cetera, et cetera. And then you can simulate and also do automatic inference in these models. And then finally, differential equations are also a kind of generative model where we put a lot of prior knowledge in of how the laws of physics really operate. Now, machine learning is kind of interesting, is doing exactly the inverse. In machine learning, instead of going into the generative direction, we go into the opposite sort of predictive direction or discriminative direction, which is we feed in sort of the raw signal that we find in the world, in this case, pixels of an image, and we predict sort of the abstract properties of this input. So in this case, the properties are, let's say, which digit did we see? But it could also be other things like with the style with which the digit was written, for instance. Right? And it is in the opposite direction as the generative direction. And these two clearly are related, right, through Bayes' rule. So in the generative model, we think about, given a class and other properties, what's the probability of the data? And in the discriminative model, we say, okay, given the data, what is the class of the image that I see or the data that I see? And these are related by Bayes' rule, which we all know and love. And there's different advantages and disadvantages of these different methods. I would say you have white box kind of generative models. They're very data efficient. So they're on the left-hand side of that spectrum that I showed before. They use a lot of expert knowledge and a lot of inductive bias, let's say the laws of physics and causality. They're highly interpretable because every variable actually means something in this world. And they have good generalization, for instance, because they use the causal structure and the physical structure of the world, and so they can do much better out-of-domain generalization. Now, the black box, they're far more flexible. And so we have to acknowledge that in many cases, our imagination is limited and we cannot write down the infinite complexities of how the real world works. So think of a social network and how people interact. It's just way too complicated to write down. And so it's much better to write down a model with a huge number of parameters and let the data determine, what the real patterns are in the data. And these neural networks, they basically do that, and they allow you to put little inductive bias, but let the data determine all these things. They're very fast in making predictions, because basically you don't need Bayes rule in order to make predictions. The models are trained in the direction that you're actually making use of them. And they're also highly accurate, and basically at this point, they're the best models for many tasks. All of this is connected to what we call inverse modeling. When we do inverse modeling, we start with an image, let's say, or something we observe in the world, and then we have an encoder model, which basically tells us, how this thing looks like at the measurement level. So this is the ground truth world, and then the measurement basically looks like, some kind of a corruption process. And then there's the inverse model, which then says, okay, take the measurements and predict back for me what the original data looked like. And there's many exciting examples like this in the field of inverse modeling. So here's an example that we've worked on a little bit, which is radio astronomy. So you have some latent model of the sky where there are certain sources that emit radio waves. This is not what you measure. What you measure is in the Fourier spectrum. And in fact, you're not even measuring in the Fourier spectrum. You're measuring a very sparse subset of the Fourier components in the Fourier spectrum, because you have these antennas, and there's only a finite set of those. And then, of course, you could naively think that let's just do an inverse Fourier transform, as this was a forward Fourier transform, and you find that that's a very poor reconstruction. And so what you really want to do is either go from here to here to do a good reconstruction of this, and of course that's where you want to use some kind of deep learning. Very, very similar is MRI. So in MRI, again, I have some latent structure of a brain, and then we model or we measure. So we measure in the Fourier domain. So the sensors are basically measuring in the Fourier domain. We really measure a very small subset of those Fourier components, and then the task is, how do we reconstruct this image? If you do a naive thing, you'll get a very poor reconstruction. And then finally, there's error correction decoding. So I have some kind of message that I want to send, like a bunch of bits, in this case organized as an image, and I'm going to add some redundant error correction bits to it. I'm sending all that over a noisy channel. So that's our sort of a decoder. It will give me this thing, and now the inverse model is to clean it up. So to go from here, to map from here to here. It's complicated, but we can do it, and we can basically get the clean image back. So what are the traditional solutions to these types of problems? Typically, you write down your measurement model, which is P, Y given X, which is your sensor model. You have some prior over the input domain. This could be the images of the sky or the MRI images. And then you do basically gradient ascent on this sort of objective to find the most likely image X, which can explain the data Y. That's basically this very simple iterative algorithm. More sophisticated algorithms are something like belief propagation, where you will, again, send messages. You represent your problem as a graph, and you send messages on this graph. And this is what's called belief propagation. Anyway, all of these are iterative optimization schemes. Now, the deep learning solution is, again, the flip side of this, which is I'm going to not try to model anything explicitly. I'm just going to collect a huge data set of points X and Y, where X is the sort of input, the noisy input, and Y is the reconstruction. Sorry, the opposite, in the other direction, Y are the observations, and X is the sort of the clean input. And then I'm going to train some neural net that takes the noisy input and predicts a clean image X out of that. And so the one very sort of well-known algorithm that does that is the UNet. There's all sorts of convolutions running inside this thing, and there's downsampling and all this kind of stuff, skip connections, and then in the end, you'll find some kind of segmentation or reconstruction of the original image that you've done. So importantly, this is just a learning-based approach, and you need a huge amount of data to make this train well, and it doesn't use important information about the generative process, which goes directly from X to Y, which is the measurement process. Okay, and so the hybrid solution that we worked on, or the question that we wanted to answer is, okay, how are we going to embed this generative process into the guts of a neural network? And so there's a couple of things that we base that on. We basically say, well, each one of these sort of classical algorithms, like this one, they are iterative optimization schemes. So let's use that iterative optimization scheme as the core, the backbone of a neural net, or an RNN, a recurrent neural net. And then train a neural network around that backbone to correct for the mistakes that the backbone sort of solution is making. So now we're not trying to, like here, try to predict the entire signal, which could be highly nonlinear and difficult. We're just trying to predict the mistakes that the original sort of inference network is making, the engineer's sort of solution, the classical solution is making. And since we're in an RNN, we can also add a whole bunch of memory states, S, to store information, because now we have an RNN sort of set up. Now the classical solution that we want to build around is a message passing scheme that works on graphs. And of course, we like it because we already know that a graph neural net also sends messages on the graph, and so they're easy to compute. So here's what we call a vector graph for low density parity check codes. You have some nodes which are variables, and you have some factors which basically relate the bits which are on these nodes together. They basically say they have to sum up to 1, for instance, or to 0, so that they form a constraint on these bits. And then in order to decode, you have to send these messages over this graph using belief propagation, and then you'll find the most likely explanation of, for this particular bit on this node, given all the evidence that you're seeing and given all the constraints that you have put in your model. And that's basically what a low density parity check error correction decoder is based on. So to remind you again, our graph neural net also sends messages. So I already treated this graph. So it's just normal convolutions, and graph convolutions are just sending messages on a graph. So that's very similar to the other message passing scheme. And here I've written out the equations. If you don't like equations, you can skip it. But basically you have HI and HJ, which are the two vector feature representations at 2 nodes. There's some feature which lives at the edge. You push it through some neural network to get some message on a particular edge. In this case, going from this node to this node. And then you collect all of these messages together to get your new sort of message here, and then you push that through a nonlinearity to get your new feature vector here. So you see it is very similar to what actually normal message passing is doing. So we had to generalize that for the LDPC error correction decoding application. We had to generalize message passing on a normal neural net to message passing on a vector graph. It turns out it's not very difficult. You just treat these vector as other nodes in your graph neural net, and then you have 2 types of nodes, and you can just do whatever you did for a GNN, but then for these 2 types of nodes. It's a very straightforward generalization. Okay, so then the whole thing looks as follows. The details are probably a little hard to understand here, but just focus on the sort of the big picture. We have these blocks, which are iterations of the algorithm. So think of these as the iterations of the other sort of decoding algorithm, or the other inference algorithms. It's an iteration of BP, so we get some messages in. We do an iteration of BP. BP sends its messages to a GNN, a neural network. So they receive these messages, then they compute some output. The output gets combined with the belief propagation message, and a new message mu is computed. This is now a corrected message. So the GNN is now correcting the belief propagation messages. The vector graph also has its own internal state, which it also pushes to the next one. So because this is sort of the GRU, or unit, or the RNN unit, so it has its own dynamics. And this repeats over iterations. And then at the end, we compute our final estimate of what we want to compute. Let's say the bits of our error correction decoding algorithm. And then we have ground truth for a whole bunch of examples, and we compute gradients. And then we do back propagation on this loss through the whole chain to compute our best estimate of our neural net. Sorry, I need to drink something. Okay, so we trained this as an RNN and iteratively, and then we're going to test it. So here's a couple of examples where we can test it. So again, so what we have done basically is incorporate the generative model, which determines the belief propagation, into the guts of a neural network, which is the RNN. And so here we have a fairly challenging kind of dynamical system, which is a Lorentz attractor, which is chaotic. So this is ground truth. If you run it, if you do nothing and just look at the observations, it's this. If you run the GNN, if you just train the GNN alone, you get this. If you do an extended Kalman filter, which is a sort of an improvement over a normal Kalman filter, you get this. And if you do both of them combined, the algorithm that we propose, you get this. And in terms of error, so here is the number of samples that you give to the problem. Of course, if you give it a few samples, it's a much harder problem. And certainly the neural networks, they fail because you don't have enough data to train. And the Kalman filters, which are here, they're doing fine because they don't need any parameters to train. So they're always sort of constant. But then as you add samples, this GNN is going to do better and better because it can sort of, it can model the mistakes. It can model much better than the extended Kalman filter because there's mistakes in that model. But then if you do both together, then you can see that these curves are actually better than the both of them. And here's the LDPC error correction decoding algorithm as a function of how much bursty noise we add to the channel. So this is a normal Gaussian channel, but we're going to add with a certain probability some high variance noise, which is actually quite realistic. And then we're going to do decoding as we increase this sort of variance of this noise. And we do 5% of the time we add this noise. And then you say that you can see again that the typical classical algorithms, LDPC decoding, they do fine if this sigma isn't all that large. But if you increase the corruption, you see that they degrade much faster than, for instance, our joint model. And you can also see that the vector graph model here, again, it's much worse than LDPC in the beginning when you don't have a lot of noise. Of course, these LDPC codes are very good at that point, but then we add a lot of noise, then the model isn't correct anymore, and the GNN does a bit better. But if you do things jointly, then it's even much better. Okay, so we've also applied this to fast MRI. So that's not a graph, but that's an image. But you can come up with your own sort of the same philosophy, but then for image reconstruction, also iterative image reconstruction. We did this with Patrick Putsky. We submitted this to this fast MRI challenge that was organized by Facebook and NYU. And we actually won in the single coil track. And so there, we had some extra innovations, like we had to make this thing invertible in order to solve some memory issues and stuff like that. But the philosophy of this idea worked out really well also in this real world problem. Okay, to conclude then, so at the very highest level, machine learning is nothing else as combining inductive biases plus data to make predictions. And of course, the name of the game is how to inject the right inductive bias and the right amount of inductive bias for every problem. So we can look at symmetry and sort of convolutions, or an implementation of translational symmetry, or an implementation of the inductive bias that the world is translational symmetric. And we've looked at graph convolutions, which handle typically permutation equivariance, but if we do this on a mesh, then that group was too large, and we identified basically the proper symmetry on a mesh, and then implemented that as mesh convolutions. And then the other one was neural augmentation, which is hybrid classical belief propagation message passing, plus some GNN to correct for the errors. We can apply it, and we have applied it to error correction, decoding, nonlinear Kalman filters, fast MRI reconstruction, and radio astronomy. And there's also this really cool application that we were involved in, but was basically done by astronomers on black hole lensing. So if you take an image of the sky of a galaxy where in front of the galaxy somewhere there is a black hole, and you see these really strange warped images. And then the task is to reconstruct the original source, which is behind the black hole. and we all applied this particular technique, and we got state-of-the-art results there. And also an interesting application of this could be to COVID-19 contact tracing, where you have a graph which evolves over time, and you also need to do inference in that graph to figure out who you predict is infected or infectious. So it's also an inference algorithm on a graph, and perhaps these ideas could be meaningfully sort of applied to that case as well. And that's the end. If there's any questions, I'm happy to answer them.
Wow, so maybe I can take over. Thank you very much for the talk. Very, very impressive. So for anyone who joined late, if you're following the live stream, you can enter the chat and ask questions there. I will go through them now and relate them to Max best as I can. So yes, many people say, thanks for the very nice talk, of course. Applause, applause. One question from the beginning relates to causality and asks to which extent you're also looking at causal inference. So I'm guessing because basically causal structures can be represented as graphs as well. Can you comment on that?
Yes, so we are actually in a different project, also looking actually explicitly at causal inference. So, so that's unpublished work. But what we do there is we have an encoder. Let's say you have a whole bunch of sort of objects which relate to each other in some way, maybe particles which move through space, and you want to figure out who influences who in this graph. So you say basically that the balls they evolve under some kind of interaction where one could either influence the other, or the other could influence the first, or they could influence each other, or none of them, or they could not influence each other. There's 4 choices, and you have and you want to predict, first of all, what is the actual what is the actual interaction structure, and then given the interaction structure, try to predict the future, right? And so there so I would say that therefore the causal problem is to figure out precisely, what's the structure of the graph, right? Who is influencing who in this graph, in which direction, and whether there is an interaction in the first place at all. So that to me is the causal question that you can ask here, and then you can send the messages in the direction of the causal direction. But in this work, we haven't looked at that, but that's certainly something that we will try to write up for NeurIPS.
So that's basically a problem where the nodes in the graph are fixed, but the edges need to be found when you talk about causal inference, if I understood correctly.
That's right. Yeah, so I think that's correct, yes. It's like you try to figure out the interactions and the direction of the interactions on the graph. Yeah.
How do you generally work with changing topologies? So that question came up in the context of meshes. Is that something you can do? So you mostly talked about equivariance. Can you also work with changing topologies? Like maybe splitting up polygons, if you will.
Yeah, so there's the topology of the underlying manifold that we're trying to approximate with the mesh. And I think we can handle different topologies there. It could be a sphere, it could be a donut, or it could be a, any other genus sort of surface. I don't think that's an issue, although the particular group under which we need to be equivariant might change for particular cases. The topology of the mesh, so we used basically a mesh where every edge has 2 faces on either side of it. And for that, it works nicely. If you're going to mess a lot with that, then you have to make sure that the mesh at least represents an approximation of a manifold. But you can make meshes which are not representative of an underlying manifold. And I guess that's really something that you have to respect. Otherwise, I think that's not a big issue. You can use very different meshes to do these computations, and they're not very, clearly one mesh could do better than another mesh. But you could, for instance, learn the mesh. We haven't even tried that, but that's come up. You could say maybe in certain regions of space, we don't need a very detailed mesh. In another regions of space, we need a very detailed mesh, so we can move by learning the points of the mesh around to further improve the performance.
One question that was, I think, also asked in the context of meshes says, could we use node ordering or different messages per node if the graph is weighted?
Let's see if I understand that. Different messages per edge, or different messages? Was that the question? Node ordering.
No, so it just says
there is a node ordering in the sense that on a mesh you can go in a circle, right? And there's an angle that you can define, and you can just order the nodes by the angle at which you sort of go through them. So let me maybe go back to that. Or maybe I should. Here. Right. So for this particular one, you can clearly see that you can define angles, and if you go in the order of those angles, then that's an ordering. The only issue is that you don't know where the angle theta equals 0 is necessarily, right? So there is no uniquely defined sort of absolute frame in which you can say, okay, this is horizontal, or because if you go around and you come back, then this thing has changed. And for certain topologies like spheres, you cannot get rid of it typically. So you have to. So the ordering is there, but who is at the angle theta equals 0 isn't clear, and so you have to define this equivariance or this transformation property for that particular sort of symmetry that you have in your network. The symmetry that the sort of the absolute value of your angles is not, you cannot know, doesn't exist. I hope that answered it.
Yeah. All right. Also, if I'm relating the questions wrong, do feel free to correct me in the chat. Another question. Let me go through them. One question. I think I'm going to just read them directly. For the mesh neural networks, distance between nodes is typically meaningful, both between center node and each neighbor, as well as between adjacent neighbors. Have you looked into equivariant convolutions incorporating distances?
Yeah, that's a very good question. So in this particular work, we wanted to be as simple as possible. So we wanted to keep things, one of the goals was to keep things as close as possible to a GNN, right? So the GNN is below here. Let's see, laser pointer. So the GNN is below here. And we wanted to make it look like a GNN as much as possible, but it's entirely true. And so basically what we just focused on is the angle theta, but you can see there is a little bit of a distance sort of dependency in the sense that we have, the self interaction, which is at the center at distance 0, and then everything else, which is a very, very, very rough, clearly function of distance. But you can be much more sophisticated. So you can make this kernel depend actually on the distance r as well. So you could, for instance, have different layers, different sort of bands in which you define a different kernel k, or you could even make this thing a function, like some kind of function of r that modulates that. So yes, this is a fairly straightforward generalization of what we did here. However, we chose not to do it. First of all, we tried a few things, but it didn't really improve the performance. And we really wanted to be as simple as possible and as close as possible to the graph neural net, so that we sort of stuck with this formulation and so with the hope that if we kept things simple, that people would actually start to use it.
All right. Another person asks if you generalize your work on meshes to higher dimensional manifolds.
Yeah, that's also a good question. Again, it's fairly straightforward to do it. You have to the group which was SO2, which we had to be equivariant to, will then is going to be a different group. Yeah, it's a lot of work, right? So if you do it, then you have to really think about how to mesh things in higher dimensions, and and these groups get more complicated and all this. So we picked the application where where most of the application, we picked the dimension where most of the applications are, especially in the medical domain. I'm hoping that many of the problems are actually surfaces in 2D. I mean, it's very hard to even imagine like a curved space in 3D, right? I mean, it's not so easy to to visualize what that means. And so I think we sort of capture 90% of all the interesting cases with this particular one. But anyway, mathematically, it's certainly very doable to also go to higher dimensions.
Cool. So regarding part 2, someone asks, did I understand correctly that you only model the noise generation, not the latent distribution, and that this means that you therefore need ground truth data to train a model? How can you get such ground truth data, for example, in MRI?
Yeah, okay, that's an excellent question. Yeah, so for MRI, it's actually interesting. So what you do there is, so notice that the problem is the problem of fast MRI. So basically the problem is to take a small subset of your measurements and then try to reconstruct the image from that small subset. So in a normal MRI data set, you have many more Fourier components that are being measured, but the time you spend in an MRI machine is directly proportional to how many of those Fourier measurements you're making. So the idea is that you use ground truth as basically the high resolution image you reconstruct if you use all the Fourier components and you use the best algorithm out there that uses all these Fourier components. And then basically what we say is, well, let's say if we take 1/6 or 1/8 of these components, what can we still get close to the one that we reconstructed with all of the Fourier components? So that's how you can get ground truth there. Similarly for error correction decoding, right? In error correction decoding, maybe this is a good example here. You can generate a lot of data, actually infinite amount of data, by taking bits, sending them through a noisy channel, and then measuring the noisy bits, but just storing whatever you send, right? And in communication theory, that's basically what you do when you send a pilot wave. A pilot wave is exactly, everybody knows what's being sent, and you observe what you get, and that gives you information about the channel, right? And and then using that particular channel, you then try to do the decoding. So again, here to train up these neural networks, or these sort of enhancements of these neural networks, you can just use that particular data that you generate by these pilot waves, for instance.
All right. Another question, if you still have time. What is missing if you apply an isotropic graph convolutional network on a mesh? Do you mean isotropic graph convolutional network are not powerful and efficient enough in general?
Yeah, so maybe it's easiest to answer the question if I would sort of reflect it back and say, if I would tell you for image analysis, the only filter you could use is one that is isotropic. So that's a filter that is basically the same in all directions. It's like just has radial dependence, right? Then you couldn't do, you would lose out on a lot of really important features like Gabor filters and all these kind of things you could not represent. So it's like the set of filters that is isotropic is just very much smaller than the set of filters which is, general, which can represent, direction. And so we have this equivariance constraint, which means that it's, there is some constraint. It's not as flexible as a CNN, because in a CNN, an absolute directions mean something. So we have to have that constraint. But still, the degrees of freedom are a lot more than the one you would have for a GNN, which is isotropic. And so you can compare this with a group convolutional neural net under rotations versus a normal neural net. So clearly it's a bit, you put some constraints on this because you want things to transform correctly. But if the data actually has this particular property, then it can actually be useful. But in general, it's much more flexible than if you would use isotropic filters.
All right. Someone asks, what are some ways to order nodes in a graph convolution which you tried before settling on a single K for all neighbors?
In which to order? For a graph neural net or for a mesh neural net? For a graph neural net, it basically doesn't matter because you send the same message, so everything is explicitly order independent. It's basically the neighbors are treated as a set. So whatever order you feed them, it doesn't matter, it doesn't change the outcome. For a mesh neural net, you just have to pick one node as your reference node, and then basically demand equivariance, and then you're good. And again, the answer will not depend on which node you picked.
Maybe they meant if you don't treat them all the same in a regular graph neural network.
Okay, but then you're somewhat into trouble, right? Because how you then do sharing? So if I think of a graph neural net, if I have graphs which are always the same and you have many instances in your data set, you can certainly do that. But if you would have, let's say, a very large graph, one single graph on which you would want to learn, or you would have many graphs, but they are very different shape and form, how are you going to share your filters? It's not clear if you say, well, every neighbor can send a different message, because for the next point, there's a different number of neighbors and they're in a different order. So what does that mean, right? I have to pick some ordering then, and now the result is going to depend on this very arbitrary choice of ordering that I picked. And so I can get arbitrarily bad results by picking a bad ordering there. So yeah, so I think it's so it's not really well defined, or it's not so clear what you would do in order to share your filter.
Right, makes sense. Maybe I can ask a question that's related to the fast MRI challenge. Do you remember how the K-space was subsampled?
Yeah, so that's not really my cup of tea, but I do know that, let's see if I can find it here. So where is the K-space? Okay, I didn't quite show it here, but the subsampling happened basically by having a larger number of Fourier components in the middle, and then subsampling more and more for the higher frequency ones. Now, clearly, this is something that was in the challenge, right? So the challenge, so these were actually physicians that knew precisely what they were doing, and so they had some protocol of that subsampling that we basically used. And you can probably just look it up at the Fast MRI sort of website.
Right. Because it looks a bit random. So the question I wanted to ask is if you've thought about combining your method maybe with some more advanced MRI technique like fingerprinting, if you're familiar with that.
Yeah, I don't know about fingerprinting, but this is the state of the art, though, right? This is basically the best. We won this challenge in the single coil, and in fact, we also worked with Philips, who had their own neural net which was different from ours, but also based on somewhat similar principles, where they also used these data terms, these data consistency terms, as they call them. And it's also based on a deep neural net. So I think really the deep neural nets right now are the state of the art in this image reconstruction, at least for this sort of low Fourier sort of sampling case. I don't know. There's of course also things like compressed sensing, which are very good, but still these deep learning methods beat the compressed sensing methods hands down, I think. So about fingerprinting, I don't know. So I cannot really say anything meaningful about that.
Right. No, that would be a different acquisition method. So that was more targeted towards actual application later.
Okay, so what is interesting, and we are working on that, is to do active acquisition. So can you come up with ways to a policy basically to sequentially capture the right Fourier components and do it in a way that is better than if you would predetermine this from the beginning, and even better, do it in a way that works together with the particular reconstruction method that you have chosen. So there's two components, the reconstruction method and then the active acquisition method. And it becomes kind of like a reinforcement learning problem where your task is to, after a small number of acquisitions, to get the best possible reconstructions back. And you can do that by improving your reconstruction method, but you can also improve it by your acquisition method, basically. And this is, I think, a very interesting problem that also exists in astronomy, because some of these telescopes, these antennas can be moved around. So you can change your acquisition as well. So this is a very interesting topic.